So in this video, we're going to look at how to calculate work problems involving tanks. We're going to start out with a simple case, and then we're going to talk a little bit about how to do this when the problem is not quite this simple. But the general procedures are going to be somewhat similar. So let's start with a rectangular tank. This is about as easy a tank problem as you could possibly get. Consider a rectangular tank with a base of 5 feet by 6 feet and a height of 15 feet. How much work is required to empty half the tank if the tank is full? We're going to assume the density of the water is 62.4 pounds. Again, this is typically given in the problem, or it's given as 9,800 newtons per meter cubed. Again, depending on whether you're using SI units or English units. A lot of textbooks will stick to either just the English units or will flip back and forth. So they will have to specify someplace, sometimes in the chapter or in the problem setup, what density of water you're going to need to use for that problem. One danger of like looking it up in a table or something or remembering it from another course is that in a calculus textbook, the answers are based on given the information that they are given and not necessarily general sort of general information you might look up in a table or someplace. The numbers are often rounded to a certain number of significant digits. So 9.8 meters per second squared for gravity and not 9.81 or whatever additional decimals would be more accurate. So you need to use the problems, the units that are given in the problem. If you're using a different kind of liquid, like say oil or something like that, again, you will have a different density value, but typically these will be given to you in the problem. Now, to calculate the force component for our integral, we need to calculate the volume times the density. Now, the volume is the thing that is going to potentially change, the volume of a thin slice, right? The density is given as the density of the liquid, so that's a constant. The volume in this case is basically going to be based on the area of a surface of a slice, cross-sectional slice, times dx or dy. So in this particular example, the base of the tank is 5 feet by 6 feet. So there's a rectangle on the bottom of the tank, 5 by 6. The area of that cross-sectional slice is 30 feet squared. And then to get the volume, you would multiply by a thin slice dy. So that will get you your force equation. In this case, it's 30 for the area, dy makes it a volume, and then 62.4 is the density. And that's what gets you the force. Now, for a slice, now think about slicing it at a particular value that's say y units off the base. How far do you have to pump that slice in order to get it over the top of the tank? So if you are at a height of y from the bottom of the tank, then if the tank is 15 feet deep, then to get it pumped over the top of the tank, then you need to travel 15 minus y feet. So if you're at the very, very bottom of the tank, you have to travel the whole 15 feet. If you're halfway up the tank, you only have to travel 7.5 more feet to get over the top of the tank. So that distance that you have to travel, again, I'm measuring it as 15 minus y. Now, again, this depends on how you set up your y values. If you set 0 to be at the top of the tank, then this is just y, and 15 is the bottom of the tank. But again, mathematically, I like 0 to be on the bottom and 15 to be at the top. And so my distance traveled is 15 minus how far I started up the tank already. And so when I put this all together, my integral, I'm going to just pump out the top half of the tank in this example. So if I'm only pumping, if the tank is full and I'm only emptying the tank halfway, then I'm just pumping the water out of the top half of the tank. So I'm going from basically 7.5, which is 15/2, to 15. This 30 times 62.4 dy was my force. And then the distance that it's traveling is 15 minus y. If you combine all of your constants and then you integrate the y component, you do a little bit of arithmetic because you've got fractions here. What you end up with is 52,650 foot-pounds. Now, if we were pumping out, if the tank was only half full and we were pumping out the water from the bottom of the tank, then the force, this whole integral would basically be exactly the same, except our limits of integration would go from 0 to 15/2, 7.5. And then we may not get the same value because we're pumping the same amount of water, but we're pumping it further than we were before. And so the work is probably going to be higher. Logically, it says it should be higher. Now, this is sort of the basic setup that we always have to do when we set up a tank problem. The issue that we're going to run into is basically in terms of this cross-sectional area. So in a rectangular tank, that cross-sectional area of every slice is always identical. And so we get a constant for that cross-sectional area. But when we calculate other sizes of tanks, other configurations, then the cross-sectional area is going to change for every slice. And so we want to look up how do we replace that 30 in this problem with different configurations of tanks? How does that cross-sectional area alter? And so rather than set up a whole bunch of different problems, we're just going to talk about that one particular issue because that's the only thing really that changes. Now, if the base is cylindrical, so you have a cylindrical tank, it's basically going to work very similarly to the rectangular tank problem. The only difference is that you're going to use pi r squared as the area of your circle. If you have a circular cylinder, the cross-sectional slice is circular. And so you would know what the radius of the cylinder is. Again, you might be given that information in terms of diameter, but you can convert that easily to a radius. And then you just plug it into your pi r squared form that you would have a pi floating around in your answer, but it would be a constant, just like the rectangular tank example. And so everything else would remain the same. But you do have to be careful about the units. Again, are they giving that information to you in terms of the diameter or the radius? And then the other thing is occasionally you will get problems where most of the problem is described in feet, and then they will say, well, this is basically a pipe that's only 6 inches in radius. And then you have to convert those units to feet. So and make sure that your units are consistent. But that's basically the only thing that you have to worry about. Now, for a conical tank, it's a little bit more complicated. As you take a slice, you are in a circular cone, you are going to get a slice, which is a cylinder. Again, approximately a circle times the dy, to get the volume. But that radius of that circle is going to change as you go up and down the tank. And so what you're going to have to do is you're going to have to do a similar triangle to find the relationship between the radius of the circular slice and the height that you are on the tank. So in our conical example here, I've said the radius was 5 feet and the height was 25 feet. And so translating that into just a triangle, think about it like cutting the cone in half, and then I'm taking a cross-sectional slice to get this relationship between the height of the cone and the radius of the full cone. And then at any point along that cone, I have the height, which is the distance in y from the bottom, and then the radius at that slice that I'm interested in. And I just use proportions based on the properties of similar triangles in order to find the relationship between the radius and the height. And so radius over height in the bigger triangle is 5/25, and that ratio will stay the same in the smaller triangle, r over y. And then I just use that to solve for y, and I end up with that the radius is 1/5 the height. So if you've gone up one foot essentially, or 1 meter, or whatever the unit is, then your radius will be 1/5 of that. If you go up 5 feet, it'll still be 1/5 of that. If you go up 25 feet, it'll be 1/5 of that. So all the way up, you're going to end up with the radius is 1/5 of the distance that you've traveled. So if you plug that into your the cross-sectional area formula, which is a circle, remember, because we're using approximations of cylinders, then that pi r squared, the r squared gets replaced by, in this case, y over 5. So we have now a radius for our cross-sectional area, which is determined by how far we've gone up the tank. And then we can integrate dy so that for each slice we take, as we get further up the tank, the slice is larger, but it has to travel less far. Again, coupling that with how the distance that you have to travel, which is calculated the same way as the rectangular tank problem. The only thing that's changed here is, again, that cross-sectional area that you need for the force. Now, if you have a spherical or hemispherical tank, you want to think about the cross-section of the circle, of the sphere basically being a circle. And if, again, you're thinking about a sort of a standard circle, let's say the center is at the origin, then how far away are you from the center if you are at a certain height y, certain distance from the bottom of the tank? Basically the radius at that point is x, right? And so you want to relate that relationship between x and y, which is just the equation of the circle. Now the problems here can get a little bit more complicated, again, depending on where you specify your 0 to be. So you want to think about those somewhat carefully. But that relationship between the x, which is the radius that we want for our cross-sectional slice, that comes from this relationship of the circle. So if our tank has a radius of 12 feet, then our radius equation is going to be x squared plus y squared is equal to 144. And so x is the positive length, it's the radius, because it's not a position, it's just a distance. It's 144 minus y squared. And so then we would plug in the square root here into our r for our cross-sectional area, and our volume component would then be pi times 144 minus y squared. The square in the cross-sectional area and the square root cancel each other out. Now, if your circle is positioned at some point other than, let's say, the center at ground level, but maybe it's positioned someplace else, maybe it's off the ground, then you can adjust your y value. Again, the x value it's relative to wherever the center of the tank is. But the y value can be adjusted so that if your circle is, if your center of your tank is off the ground, then you put the center someplace, and that will adjust your equation a little bit. There'll be a little bit more algebra that you'll have to do, but basically the reasoning stays the same. So in this case, the water tank is 25 feet off the ground. That assumes that the bottom of the tank is 25 feet off the ground. And so the center is actually 12 feet further above that because that's the radius of the tank. And so the center is at 37 feet off the ground. But again, keep in mind how you are setting up your limits of integration. Make sure that if you're pumping out like the top half of the spherical tank, the way that we've set this up, 0 is in the center in the initial setup. And so you might have to pump from -12, which is the bottom of the tank, to 0 in order to get your limits of integration to work out. Typically, when you're dealing with a hemispherical tank, the tank is considered to be like the bottom half of the sphere. But depending on how the problem is worded, it could be the top half of the sphere. And so just be aware of that as you set up these problems. But those are the sort of the main thing you have to worry about is how do you get that cross-sectional area? That's the hardest part of the tank problems when they go to these cones and these spheres. The general setup is very similar in all the tank problem cases. It's just that area that could go from a constant to a formula, and that will change from problem to problem.